Okay, so let's start today's topic. So, uh, so last time think I finished the first part. So hold on. Yeah. So think last time I finished the part where it says yeah. Yeah, maybe about a little, but I just leave the rest part to you. Okay, I think I've kind of finished the part B. Okay, and let me think. Kind of fee is okay. So what is kind of fee? So kind of fee is okay. So last time I think I just solve it here. Maybe kind of fee is equal to not. So what is kind of fee? So kind of fee is uh, oh yeah. I think I showed that right. So this is equal to gamma of this alpha tilde something like x naught, where alpha tilde is the path from 0, 1 to this x tilde, such that from x tilde to from x tilde, so from x tilde to phi of x tilde. Uh, okay. Anyway, I think I showed this. Okay, I think I showed this. Okay. So yeah, so let's move on. Okay. So let's start with the definition. Okay. So again, there are like 3 more parts. So okay, so maybe let me think. Okay, so maybe I'll try to maybe spend like 1 or 2 lectures proving this CDE. Okay. Okay, so let's take the part. Let's take the part C. Let's see. So okay. So again, I think I showed the part B of the theorem last time. Okay, so let me just start with yeah. So let me start with part C. Okay. So part C. Remember we have same setup, right? So we have the gamma from this x tilde to x. Yeah. So we have this gamma from x tilde to x. So universal covering. And then we have this f as a fiber, right? For the base point x naught. And then we fix we'll fix a point in the fiber x tilde. Okay. Sorry, x naught tilde. Okay. Okay, so let's start with part C. So let sigma to be defined as the chi inverse. So let me run. Yeah. So I think I just know what chi is. So I just don't write out. Okay. Chi inverse from this pi 1 of, yeah, because we showed last time that this chi is a inverse, is a isomorphism actually. Okay. So therefore we want to show that this one is a yeah, so it's an inverse. Yeah, it has an inverse. Okay. All right. So now let me think. Goes from pi 1 x naught to the deck transformation of this gamma be the inverse isomorphism. Okay. So if x is in x naught tilde, so pick a point x in x tilde, and then this gamma tilde is a path from x naught tilde to x. And then we have this this alpha because alpha is based on x naught, right? Wait. Okay, sorry. Yeah, alpha is based on x naught is in pi 1 of x naught. Okay. And then this alpha tilde is the unique lifting of alpha to a path in x tilde with alpha tilde 0 equal to x naught tilde. Okay. Alpha tilde is the unique lifting of alpha to a path in x tilde with alpha tilde 0 equal to x naught tilde. Okay. And gamma and this gamma tilde 1 is the unique lifting of gamma, which is defined as the big gamma of gamma tilde. Okay. Small gamma. Okay. Small gamma 1 is the unique lifting. Lifting of this gamma, small gamma, which being defined as the big gamma of gamma tilde. Okay, so to a path with what? With this gamma tilde 1, 0, which is equal to the alpha tilde 1. Okay. So then we have that this phi of alpha, the homotopy equals called alpha centered at x naught, evaluated at x is equal to okay, gamma 1 tilde at 1. Okay. So yeah, so that is this phi of this equivalent scale of alpha centered at x naught evaluated at x is equal to the terminal point of the lifting of this alpha product with gamma with initial point x naught tilde. It's the terminal point. Of the lifting of this alpha product with gamma with initial point x naught tilde. Okay, so let me draw a picture here. Okay, so let me draw a picture. So okay, so here you fix a point. So let me draw the lifting. Okay, so this is the space x. Okay, and then you have the space x tilde. This is the projection gamma, and then big gamma. Okay, and then you pick a point x in this x tilde. And then, so suppose that here is the base point x naught, and then you have the fiber here, and then you have this point as, let's say, x naught tilde, and then you pick any point x in this x tilde. So here you pick a point, let's say x here, and then draw a line here from x naught tilde to x. Okay, so here in this direction. And then we call this gamma tilde. Okay, so now the thing is that, let me think. Okay, so here you fix a point, you fix alpha. Okay, so alpha is a loop. Okay, so this is like alpha here. And then, let's see what happens. So then, this alpha tilde is unique lifting of alpha to a path. Okay. Alpha 0 equal to x naught tilde. Okay, so here you have a unique lifting, right? Okay. Yeah, and then gamma 1 is the unique lifting of gamma 1 tilde is unique lifting of small gamma 1. Yes, small gamma 1 tilde is unique lifting of this small gamma, which is equal to the gamma of gamma tilde. Wait, what? Oh, okay. Okay, so yeah, so what we do is that, okay, so what is gamma of small gamma? So yeah, so remember this gamma is a path, right? It's a path. So when we apply gamma to it, it becomes a path downstairs, right? So here, let's say that this is like small gamma, and then to a path with okay, so gamma 1 tilde is the unique lifting of gamma to a path with oh, okay, yeah. So here you leave this path, okay. So you leave this path to a path with this initial point alpha tilde 1, okay, which is the endpoint up here. So basically what you do is that you do a lifting like that. Let's say yeah, this is the lifting. Okay. Okay, and then then what? Then what you have is that to a path with okay. So then you have this phi of alpha x naught x is equal to wait, what? Okay. So then you have okay. So then you have this sigma of so sigma of this alpha at like base point x naught. You got it? Okay. Let's see what is this guy. So okay. So this phi is like chi inverse, right? So okay. So this is like okay, so this is equal to the chi inverse of okay, so this is actually a Lex transformation, right? So of x. Let me think. And then I want to show that this one is equal to small gamma tilde 1 of 1. Okay. So let's see why it's true. So we know that this chi of any function phi is equal to it's being defined as yeah. So I just define. So it's equal to like the gamma of this alpha tilde, right? Alpha tilde, okay. Alpha tilde, where the base point is x naught, and then okay, yeah, and then where this alpha tilde is start at x naught, and then end at phi of x naught, right? Oh, sorry, x naught tilde, yeah. Okay, so now what happened? So I want to show that. Okay, so if you have a path, let's say, okay, Okay, so I want to show that this one is equal to that. Okay. So yeah, okay, so namely this one is a so this one is a map, right? So this one should be this one should be a map, right? So again, like I said, oh sorry, what I'm trying to say. So okay, so basically, wait, hold on a second. Okay, so okay, so I know that. Okay. Okay, I know that chi of this map, right, is equal to okay, so let me see. Okay, because this chi inverse is this chi is isomorphism, so this chi inverse, so that is denoted by this phi theta, and then we know that chi of phi theta is equal to okay, yeah, but by definition, this chi of phi theta is equal to that with this alpha being defined as that, and then we also know that we also know that this gamma of this alpha theta is a loop, is homotropic to this alpha, right? Okay, so that means that what? Okay, so I want to show that this okay, I want to show that phi of x equal to 1. Okay. Let me see. Let me see. Okay, so want to show. Okay, so let's see from the picture what does this looks like. So okay, so here I have a phi, right? So phi is whatever this sorry. So phi is like a chi inverse of this alpha, yeah. And then I think okay. So and then so chi of phi is equal to So basically, this phi tilde is a Dirac transformation such that okay, so the only thing we know is that okay, so this alpha tilde 1, wait, so this alpha tilde is not the same as this alpha tilde, okay? So maybe I'll use alpha tilde prime or something, yeah. Okay. Okay, so okay, so the only thing we know is that because yeah, okay, so because the thing is that okay, so what I want to show is that I want to see whether this point I want to say what is this point, okay? You want to see from some information about this phi. So, okay, I know that this, to know this one, I want to know something about this alpha tilde, right? Alpha tilde prime, yeah. So, okay, I know that this alpha tilde prime is homotopy to alpha. Okay. Wait. It is homotopic to alpha. Okay. Okay, so let's use this one as alpha prime. Okay. So basically you have this alpha prime homotopic to alpha. Can you say that upstairs are also homotopic? I think so, right? Because if you have like two curve being homotopic, wait. So if you have two curves being homotopic in the base space, then yeah. So and then they share the same. Wait. Okay. Okay. Okay, I think this is true because by the path homotopy lifting property, okay. So so since this is homotopic, right? So this alpha prime and yeah. So let me write out. So so since you have this alpha prime is homotopic to alpha, so there is a homotopy h of s x, and that this h of yeah. So h of the initial point, which is alpha, and then okay, and then yeah. Okay, so now let's see what happens. So now, so since you have yeah, so since you have this okay. Okay, so by definition, so there is a unique lifting. So by the homotopy path lifting property, okay. Sorry, by the path homotopy lifting property, so there is a unique lifting of this path such that this so by the path homotopy lifting property, so there is this unique h from A to this x tilde such that this h of this h 0 is equal to in your point, okay, is equal to this x naught tilde, okay. So then by the unique lifting property, okay, by the path unique lifting by the path unique lifting property, we must have this we must have this this h of, so then by the path unique path lifting, so we have that this h tilde of t 0 should be equal to what was I saying? So must be equal to alpha tilde, right? Because we define the alpha tilde to be the unique lifting of alpha with initial point x naught tilde, okay? And then this h of 1 must be equal to this guy, right? Alpha tilde prime, okay? Because by definition, yeah. So then, let's see what happened next. So, yeah, so then I know that these two are homotopic. Okay, so therefore, this implies that, so this implies that this alpha prime and 1, they share the endpoint, same endpoint, right? So which is equal to this alpha tilde 1, which is equal to, what is alpha tilde 1? Okay, alpha tilde 1 is alpha tilde 1, right? Okay. Okay, so okay. Yeah, so okay, so we know that this phi, okay, this phi of this x. Okay, we know that this phi of this okay, so this implies that this phi of this phi tilde of this x naught tilde is equal to this alpha tilde 1. Okay. So what happened with this phi of this x? Oh, okay. Wait. Okay, so I want to say something about this image of x. Okay. Okay, so okay, so yeah, so let's see. So this is like a phi of this x naught tilde, right? And then what we have? So yeah, sorry, phi tilde. And then okay, so then what? Then so this phi is automorphism, right? And then it's the bijection, and then okay. Okay, so let's see. So we know that this phi of this alpha 1 tilde. Sorry, we know that this. So we know that this. Wait. Okay. Okay, so since so since we know that this since we know that this gamma composed with phi is equal to gamma, right? Okay, so now what? Okay, so now so this implies that gamma composed with this phi at so basically you plug in this gamma here, okay? Because this phi of gamma is equal to that. Yeah, this phi of epsilon is equal to that, sorry. So of this gamma of let's say t, gamma tilde t should be equal to the gamma of this gamma tilde t. Okay, so yeah. Oh, okay. So this implies that. This implies what? This implies so this implies that this phi composed with gamma tilde is a lifting, right? Of this gamma, right? Because this is equal to because this is equal to gamma t, right? Yeah. Okay. So then then by the unique lifting theorem, right? So then it has, yeah, it has an initial point phi tilde of f dot tilde. So therefore, by the unique lifting theorem, there's a unique lifting. So therefore, so by the unique lifting, you have that this phi of so at the end point should be equal to the gamma 1 at the end point, which is equal to, yeah, which is equal to the end point, okay. Okay, so that tells you what? Okay, yeah. We know that this is x, right? So yeah, I think that shows the result. Okay. Okay, so yeah, so let's move on to the next part. Okay. Okay, so for part D, okay. Part D, you have the composition. Pi 1 of x naught to dec gamma to f. Is given by okay, so is the projection given by wait, okay. Given by this alpha at x naught goes to phi of this alpha at x naught. Okay, evaluate at x naught tilde. Okay, so let's see why this is true. So you have the composition is given by wait, what was the map? Okay. Okay, so I think what he means is that so remember like before we define a map. So I think, yeah, I think what he means is that if you have this because from this stack to f, I think you have the map from phi goes to phi of epsilon tilde. Okay, so here I think here is the exactly this map, right? So you have this as an inverse chi, right? Yeah, I'm not sure how to yeah. So so this is like the chi inverse. Okay. Yeah. Okay. So is the bijection given by alpha x naught goes to that. Okay. Okay. So yeah, it's a bijection. Okay. So let's see why it's this one. Okay. Okay. So yeah. So if you have this, you start with this alpha. Okay. So let's see what is this alpha inverse of. So namely, I want to show that this alpha inverse of this one, and then evaluate at x naught tilde. Oh. Huh? I think that's trivial, right? Yeah, I don't think there's anything to show here. Yeah, because by definition, this sigma is just the alpha inverse, right? Yeah, and then by definition, this map deck goes to f. This phi goes to phi of x naught. Yeah, I don't see anything to show here. So yeah, let me see. Yeah, I think everything. Yeah, everything. Yeah, I don't think there's anything to show here. Okay, so. Okay, so now let's see the last part. Okay, last part. So part E. Okay, so part E says each element phi in this deck gamma take away identity has no fixed point. Okay. So take away the identity element has no fixed point. Okay. In fact, if U is an evenly covered domain in X, okay, domain means open connected, and then U0 is a component of U tilde, which is being defined as gamma inverse U. Okay. So if U is an evenly covered domain X, and you have U0 is a component of U tilde, which is being defined as gamma inverse U, then the set U1, which is being defined as phi of U0, is a component of U tilde that is distinct, hence disjoint from U0. Okay. Zero is a component computer that is distinct hence disjoint from U0. Okay, so let's try to show this. Okay, so okay, so let's first show that each element phi in this deck, the deck transformation group of this gamma, quotient by no, sorry, not quotient, but excludes the identity element has no fixed points. Oh, okay. I wait. I think we let me check. Okay, so what do you want to show? So, so we want to show that this has no fixed point. Okay, so, okay, so suppose